Assalamualaikum doctor, we are from group 2. In this video, we will gonna talk on generation and detection of Am-Dsbsc. So this is our group members name, which my name is AIMAN RUSYDAAN and my other friends are ABDUL, AZIIMILAZIZ and AIMAN HAFIY. So before we go through to the double sideband suppressed carrier, we need to know first where the SPSC comes from. So by the general knowledge of telecommunication principles, there are three types of modulation, which is amplitude modulation, pulse modulation, and digital modulation. In amplitude modulation, we have many AM systems, and one of it is double sideband suppressed carrier. So what is double sideband suppressed carrier? Double sideband suppressed carrier is an amplitude modulation that make the carrier component to be suppressed. There are only two sideband that exist, which is USB and LSB. Only these sidebands that are sending and transmitting information to the receiver. And the equation of Am-Dsbsc is Em over 2 cos omega c plus omega m t plus cos omega c minus omega mt. And the bandwidth of Am-Dsbsc is 2 FM. So next, I will discuss on the theory of the generation and detection of the SBSC. As we know, the SBSC signal is obtained by multiplying the original signal and carrier signal. This process also called modulated process, and the multiplier that is being used is a balanced modulator. So there are two types of balanced modulator, which is fat balanced modulator and diode ring modulator. So for the fat balance modulator, the DSB signal equation is obtained is 2MACXT cos omega CT. To get this DSBSC signal, it must have two input, which is carrier signal and information signal. The fat balance modulator is used when the input signal has a different phase angle. So by applying G1 and G2 fat in opposing phase, it will remove the carrier component, and thus it will create the DSBSC signal.
My name is Aiman HAFIY bin RUSYDAAN. Now let me proceed with diode ring modulator. For diode ring modulator, this is the diagram. It consists of 4 diodes in which all of them are pointing in the same direction and forming a ring. That is why it is called ring modulator. It also involves the setup of primary of transformer T2 here and setup of the secondary of transformer T1 here. Now let us assume that the modulating signal is absent. When A is positive with respect to H, it is positive half cycle. So diodes D1 and D2 will be forward bias, while diode D3 and D4 will be reverse bias. Carrier component of current flows through the path ABCDGH and ABEFGH. So look at here, ABCDGH and also ABEFGH. So that's why the flow is like this, and also another one is like this. Okay. Meanwhile, for negative half cycle, it will be upside down because H is positive with respect to A. So, diodes D3 and D4 are forward bias, while diodes D1 and D2 are reverse bias. So, it will flow from H until A. Okay, so this is the flow HGDEBA and HGFCBA. If both of the setups, B and G, are true setups and the diodes are identical in their behavior, there will be no carrier component induced in both half cycle of the carrier. Whenever the carrier is added with the modulating signal induced in one half of the secondary of transformer T1, the modulating signal induced in the other half subtracts from the carrier. Therefore, the SBSC signals are produced in the output with carrier frequencies of FC, 3FC, 5FC, 7FC, and etc. This is because the square wave carrier signal has the only odd harmonics. Okay, now we proceed with the detection of the SBSC signal, or we can call that as demodulation of the SBSC. It is actually a process where we want to extract the original information signal from the SBSC wave. So we use the coherent detector. Okay, so this is the block diagram of the coherent detector. In order to extract the information signal from the SBSC wave, we need to multiply it with the local oscillator that have the same frequency than the phase of the carrier used in the SBSC modulation. So the output is then passed through the low pass filter so that we can get the desired output. Okay, so that's the general idea of the coherent detector. Okay, now we let the SBSC wave as this equation and the output of local oscillator as this equation. So we multiply both of the equation, so we get the output of product modulator here, VT. Okay, and then we pass it to low pass filter, and then we get V naught T here. So when the phi is 0, it will be at maximum amplitude. Meanwhile, when the phi is plus minus 90 degree, it will be at 0. Okay, so this effect is named as quadrature null effect.
Assalamualaikum. I'm Abdul AZIIMILAZIZ bin Ahmad Dawood. So I will explain about the analysis and the discussion. For the analysis, we will consider the two signals, the carrier and message signal, and then we will perform the mixing process to obtain the double sideband suppressed carrier. So by performing the mixing process within two signal, we get the V double sideband carrier, this equation. And then we will do the demodulation process by mixing the double sideband suppressed carrier with V carrier. And then we will insert the low pass filter and we'll get the demodulated signal. Next, for the analysis of V output, which is V demodulated, we get a 4.5 cos 2 plus minus 2 pi 2t. And then we will perform the analysis by using MATLAB to obtain the signal. So here's the MATLAB script we perform. Insert all the signal into the script, then we will run the simulation to obtain the graph. So we will analyze the process by referring the graph. For the demodulation process, we will insert the low pulse filter and using Butterworth filter to normalize the frequency. For the demodulation process, here the function that we will use. And then we will plot all the signal to obtain our desired signal. So here's the result for signal wave. For the message signal, the amplitude is 2. For the carrier signal, the amplitude is 3. And here the pattern of the wave. For the demodulated signal, here for V double sideband suppressed carrier signal. As you can see, the amplitude is 6. So for the demodulated signal, we obtain the amplitude is 8.991. So here's the Fourier transform of the signal of the graph. As you can see, we will get a pair of signal for message signal, spectrum, the carrier signal. But for the modulated signal, we will get 2 pair of the signal. And for the demodulated signal, we also get pair signal. Here's the y-axis indicate the amplitude of the signal. For discussion, we will compare the theoretical values and simulation values. For voltage carrier, modulated and double sideband suppressed carrier, we get all the same value for the theoretical and simulation values. But for the output value, we got the V output is similar. For the simulation value, we get the similar output for the amplitude, which is 8.991. This is caused by the existence of the noise, and that is why the value can obtain the exact demodulation amplitude values, which is 9. And we will compare the result from the table 1 and table 2. Here's the table 2. Indicate the amplitude of frequency spectrum after the Fourier transform. Note that the amplitude of each signal from the original will reduce to half due to the Fourier transform of the signal. The amplitude of the demodulated signal is increasing after the filtering process due to the response of the narrow band. It's the demodulated signal.
In conclusion, we have known that the generation and detection of Am-Dsbsc comes from the modulation and demodulation process. So to get the DSBSC signal, the carrier and information signal must having a modulation process, and to get the original signal back, simply demodulated back the DSBSC signal by using low pass filter. That's all from us. Thank you.